In this video, I will show you how to take all of the skills we have learned so far in this unit and use them to help us sketch the graph of this rational function. But first we need to identify the places where the original function is undefined. The function will be undefined where the denominator is equal to 0. So we can go ahead and set x squared minus 4 equal to 0. We can either add 4 and take the square root, or we can factor using the difference of two squares. I think I'll go ahead and factor this time. X plus 2 times x minus 2. Using the zero product property, we quickly see that x equals negative 2 and x equals positive 2 are the two spots where the function is undefined. Of course, these are the vertical asymptotes. The next step is to use the first derivative test to find out where the function is increasing and decreasing. So let's find the first derivative. Let's go ahead and use the quotient rule. So we have the expression in the numerator and the denominator. For the quotient rule, we will start by taking the derivative of the expression in the numerator. And we will multiply that by the expression in the denominator. And then we subtract, and this time around we leave the expression in the numerator alone. As we multiply by the derivative of the expression in the denominator. But then we have to take all of that and divide by the denominator squared. So let's go ahead and calculate some of these derivatives. So we have f prime of x will equal, okay, so the derivative of this first expression here is going to be 2 times, taking the derivative doesn't affect the constant in front. So I'm just using the power rule, so I'm bringing that 2 to the front, so that'll be 2x. And the derivative of a constant is 0, so that's all gone. And we still have times x squared minus 4. All right, time to take the derivative of this expression, which again will just be 2x. And in the denominator, we will just leave this x squared minus 4 squared for now. Simplifying this down a little bit, we're going to have 4x times x squared minus 4 minus, and looks like we'll have another 4x because 2 times 2x times x squared minus 9 divided by x squared minus 4 squared. Next, I think I will go ahead and do the distributive property in the numerator and see what I get. So 4x squared times x squared will be 4x to the third power minus 16x. Now I'm distributing a negative 4x. Don't forget about the negative sign. So I'm going to get negative 4x to the third power, but then I'm going to get plus 36x. And I am going to leave this alone. So combining like terms, one interesting thing I notice is we've got the 4x to the third power here and a negative 4x to the third power here. These are going to cancel each other out. Combining like terms, we have 20x over x squared minus 4 squared. Remember that the first derivative tells you the slope of the curve at any given point. So this is going to tell us where the function is increasing and where it is decreasing. So of course the function will be increasing wherever the first derivative is positive, and it will be decreasing wherever the first derivative is negative. To find these intervals of increasing and decreasing, we will need the critical numbers, and that's where the first derivative is either equal to 0 or is undefined. So when you have a fraction, the only way for a fraction to equal 0 is for the numerator to equal 0. So we can simply set 20x equal to 0, which tells us that x equals 0. So this is a critical number. Now as far as f prime being undefined, this would happen where the denominator is equal to 0. But if you take the square root of both sides, you're going to immediately get x squared minus 4 equals 0. Is this looking familiar? We could factor this and get x plus 2 times x minus 2, which will give us x equals negative 2 and x equals positive 2. Now, why is this looking so familiar? Remember, right at the beginning, we found that x equals negative 2 and x equals positive 2 are vertical asymptotes because the original function is undefined. So these cannot be critical numbers. So we have one critical number and two vertical asymptotes. Let's go ahead and use these values to do the first derivative test and find the intervals of increasing and decreasing. Before we get started, I'm going to label this side of the axis with f prime to remind us that any calculations we do here are for the first derivative test. We're going to need some test values. So in this interval, let's go ahead and use negative 3. And in the next interval, let's use negative 1. And in the next interval, let's use positive 1. And in the last interval, let's use 3. So we are evaluating the first derivative. So we will have 20 times negative 3 over negative 3 squared minus 4, and then all of that would be squared. So what's going to happen? In the denominator, we have 9 minus 4, which is 5, and that's going to be squared. So we're going to have a positive number in the denominator, and we have a negative number in the numerator. So that's going to give us overall a negative value for this interval. That tells us that the function will be decreasing in this interval. So I'll just indicate that with a downward sloping line for this interval. So let's move on to the test value of negative 1. So now we're looking at 20 times negative 1. And we have negative 1 squared minus 4. And that whole thing is going to be squared. So look how the denominator is squared. So you know that the denominator is going to be positive. All right? Anytime you're squaring things, that's definitely going to be positive. The numerator is, of course, negative, which gives us an overall negative value for this interval. So this is another decreasing interval for the function. So moving on to positive 1. So in this interval, we will have our 20 times positive 1, and then 1 squared minus 4 squared. So as I mentioned before, we know that denominator is going to be positive because it's being squared. But this time the numerator is positive as well. This gives us an overall positive value, which means we have an increasing function in this interval. All right, and finally for the value of 3. So you can probably see what's going to happen right away. We have 3 squared minus 4 squared. So the numerator is going to be positive. Of course, the denominator will still be positive because it's squared. So the overall value is positive. Another increasing interval for the function. Now it's time for the second derivative test, which will tell us where the function is concave up or concave down. So let's find the second derivative by taking the derivative of the first derivative. It looks like we're going to need the quotient rule again. So remember, the way the quotient rule works is first you take the derivative of the numerator, which will just be 20, and then you multiply that by the denominator unchanged. So I'm going to have x squared minus 4 squared. Then you have to subtract, and you're going to take the, this time around, you're going to leave the numerator unchanged and multiply by the derivative of the denominator. So for the denominator, I'm going to have to do the chain rule. So I'm going to first use the power rule and move that 2 to the front. So I will have 2 times x squared minus 4. But that's the outer function. For the chain rule, you then have to go ahead and multiply by the derivative of the inner function, x squared minus 4. And the derivative there is going to be 2x. So the other part of the quotient rule is you have to divide by the denominator squared. So of course the denominator is already squared, so if I square this, it's going to just end up being to the 4th power. So I'm going to end up with x squared minus 4, but it'll be to the 4th power. So basically this is an expression for the second derivative. Now it's just a matter of simplifying it as much as we can. So let's see what happens. Okay, so I think for now I'm just going to leave this 20 times x squared minus 4 squared. But over here I've got 20 times 2, that's 40, times 2 is 80. So I'm going to have 80, and then x times x is x squared. And then I've got this x squared minus 4. And in the denominator, I have x squared minus 4 to the 4th power. Notice that we have this expression, okay? We have x squared minus 4 here, here, and here. So let's cancel one of these out. So there's a common factor in every single term, a common factor of x squared minus 4. So I'm going to cancel out one of these from each of these 3 places. So in these instances where we have an exponent, these exponents will be reduced by 1. And when I cancel out this one, there'll be nothing left here. So let's see what we get after we do that. So I will have f double prime of x is equal to, so now I will just have 20 times x squared minus 4, because I've taken one factor of x squared minus 4 away, minus 80x squared. That's gone. And in the denominator, we have x squared minus 4 to the third power. So I think we can simplify the numerator a little bit more now. So f double prime. So distributive property, I'm going to have 20 x squared minus 80 minus 80x squared. All right, so this is going to be negative 60 x squared minus 80 over x squared minus 4 to the third power. Let's go ahead and take a negative 20. I think that's the best we can do. Let's take a negative 20 as a GCF out of both terms. So that's going to leave me with 3x squared plus 4. Don't forget that the second derivative tells you where the function is going to be concave up or concave down. If the second derivative is positive, it will be concave up in that interval, and if the second derivative is negative, the function will be concave down in that interval. To find possible points of inflection, we need to look at where the second derivative is equal to 0 and where is it undefined. So where a fraction is equal to 0 will only be where the numerator is equal to 0. So we can solve this part of the equation by simply setting the numerator equal to 0. So dividing both sides by negative 20, we get 3x squared plus 4 is equal to 0. Wait a minute. If I subtract 4 from both sides, I'm going to get 3x squared is equal to negative 4. This is already seeming really weird. If I divide both sides by 3, I get x squared is equal to negative 4 over 3. I feel like I can stop right here. You can't square something and get a negative number. This has no solution. So far we have no potential points of inflection. How about where the function is undefined? Well, where the second derivative is undefined. That will be where the denominator is equal to 0. So let's check that out. X squared minus 4 cubed is equal to 0. If I take the cube root of both sides, I'm going to get x squared minus 4 is equal to 0. Now, this is the third time we've seen this expression. We know that this is going to lead to x is equal to plus or minus 2. And we already know that these are vertical asymptotes. So they are not potential points of inflection. Since there are no potential points of inflection, the only places where the function can change from being concave down to concave up or vice versa is at the asymptotes. So we only have 3 intervals to worry about. So we're doing the second derivative test. we might as well go ahead and use -3 again in this interval. In the middle interval, let's go ahead and use 0, okay, as a test value. And let's go ahead and use 3 again in this interval. So evaluating the second derivative at -3, the setup will look like this. So what's happening? We have -3 squared. That's going to be a positive 9. And then, so everything inside this bracket is going to be positive. I have a positive 9 times a positive 3, plus 4. That's definitely going to be positive. And then times a negative. So that tells us that the numerator will definitely be negative. Meanwhile, in the denominator, we have 9 minus 4, which is positive 5. And that's going to be cubed. It'll still be positive. So the overall result here is a negative value. So that tells us that the function will be concave down in this interval. All right, how about the middle interval? By the same reasoning as before, the numerator is going to be negative no matter what the x value is. When you're squaring things, that's going to be positive. This part will be positive. So you're always going to have a positive times a negative, which is a negative. So we really just have to worry about the denominator. The 0 part, that's gone. So now we just have -4 to the third power, which is going to be a negative number. Negative divided by a negative is a positive. So that's the overall result is positive. That tells us that we're looking at a concave up part of the function in this interval. Finally, evaluating at +3, again, we'll just skip to the fact that the numerator is always going to be negative this time. Looking at the denominator, that's going to be positive 9 minus 4. That's a positive 5. Cubed is still positive. So that's going to give us an overall negative result. And the function will be, again, concave down in this interval. So now is a good moment to look for extrema. So we're going to look for a place where we could have a relative max or a relative min. Your first stop should be scanning across the places where the function is decreasing and where the function is increasing. Look for a place where it changes from decreasing to increasing or from increasing to decreasing. Vertical asymptotes don't count. So there's only one spot, and it's right here, where the function changes from decreasing to increasing. Now, looking at the fact that the function is concave up throughout this entire interval, so you know it's sort of a U shape, it makes it all the more clear that this is going to be a relative minimum. It's going from decreasing to increasing. It's a concave up. This is going to be a relative min. Okay, so we're going to have a relative min at 0, something. Let's go ahead and find the y value that goes with it by looking at the original function. I'm going to squeeze it in right here. So I'm talking about f at 0. If we substitute in 0, the x squared part is basically gone. So we're just going to have 2 times -9. And again, x squared is just 0. So this will be over -4. So that's going to give us a value of -18 divided by -4, which reduces down to a positive 9/2. So there we have a relative min at 0, 9/2, which is 4.5. Next, we need the horizontal asymptote. That's just going to be the limit as x approaches infinity of the function. So this is just a rational function. So I'm just going to distribute to make it more clear. This is 2x squared minus 18 over x squared minus 4. So we learned back in section 3.5a that the rules for the limit of a rational function is this. So in this particular case, the degree is equal for the numerator and denominator. So the limit of the rational function is just going to be the ratio of the leading coefficients. Okay, the degree is equal. So the ratio of the leading coefficients, we're just talking about the 2 and the invisible 1. So the limit is simply going to be 2. So that means that the horizontal asymptote here is y equals 2. All that's left is to find the x-intercepts and the y-intercept. To find the x-intercepts, you set the entire function equal to 0. Well, for a rational function, we're talking about a fraction. And when you set a fraction equal to 0, all you do is set the numerator equal to 0. So we're really just talking about 2 times x squared minus 9 equals 0. Dividing both sides by 2, that gives us x squared minus 9 is equal to 0. I think I will add and do the square root this time. You could do the difference of two squares and factor. But adding 9 to both sides, we get x squared equals 9. Taking the square root of both sides, we get x is equal to plus or minus 3. So we have these x-intercepts that are going to be negative 3, comma 0, and positive 3, comma 0. For the y-intercept, we evaluate the function at an x value of 0, or in other words, we let x equal 0. So if we do that, we're going to get 2 times 0 squared minus 9 over 0 squared minus 4. So that's just going to be 2 times negative 9 divided by negative 4. So this is reminding me that this is the y value that we got for the relative minimum. We got negative 18 over negative 4, which reduces down to 9 over 2. But if we can scroll up really quickly, that's a lot of scrolling, we really already knew that this would be the y-intercept because of the 0 comma something, you know that's the y-intercept. So let's combine all this information into a sketch. So we know that we have vertical asymptotes at positive 2 and negative 2. And we have a horizontal asymptote at y equals 2. We had an x-intercept at negative 3, comma 0 and positive 3, comma 0. We had a y-intercept at 0, comma 9 over 2, which is the same thing as 4.5. We know that the y-intercept is also a relative min, and we know that the function is concave up in this interval. So we're talking about a function that looks like this in this interval. Okay, at the same time, we learned that the function was concave down in this interval and concave down in this interval. So the function is going to be, we know it has to approach these asymptotes as well. So putting that information together, it should look something like this. All right, let's take a quick peek at the real graph and see how we did. So as you can see, our graph matched perfectly with this graph right off of Desmos, including the x-intercepts and the y-intercept slash relative min, and including the horizontal asymptote at y equals 2, the vertical asymptotes at x equals plus or minus 2, and of course the intervals where the function is concave down versus concave up, and the intervals of decreasing, like here and here, versus the intervals of increasing, like here and here.